Okay, so in the last video we introduced topic 7.3, and we talked a little bit about the motivation behind the study of particle physics, as well as the discovery of the first antiparticle, which was the positron. And we looked at an image of this, and hopefully you got to see the video of the makeshift cloud chamber where you can see the tracks that different invisible particles make. So once we gained the ability to actually see these invisible particles, we started discovering a lot more of them. Okay, so remember that Dirac mathematically predicted the existence of the positron in the late 1920s, and in the early 1930s it was actually experimentally discovered along with the neutron. Okay, and so around this time we started discovering a lot of new particles. Okay, we discovered the neutron, which exists inside the nucleus in 1930. That was done by a physicist named Chadwick. In 1936, a physicist named Anderson discovered a particle called the muon in cosmic rays. Cosmic rays are basically rays that seemingly come from space that physicists seem to notice, that the higher up you go, closer to the top of the atmosphere, that the more of these mysterious cosmic rays you can detect, and they seem to be made up of different types of particles that don't necessarily exist on Earth. In 1955, the antiproton was discovered. We talked a little bit about this in the last video, but Dirac had mathematically predicted the existence of the positron. That is the anti-electron, and more generally predicted that basically all particles should have an antiparticle. Okay, and so the antiproton was discovered in 1955. By the end of the 1960s, hundreds of new particles had been discovered, and so if you thought that the only particles that existed are the proton, neutron, and the electron, you're definitely mistaken about that. We've discovered hundreds of different subatomic particles in the past 50 or 60, or really even longer years. And the way of classifying these particles comes down to what's called the standard model. Now, the standard model of particle physics is, as you can read about on the slide, a theory concerning the electromagnetic, weak, and strong nuclear interactions, as well as classifying all of the subatomic particles known. Okay, this was developed, in the latter half of the 1900s. Basically, the standard model is kind of a model of everything because everything consists of these particles. Okay, it has been worked on over many, many years. It's been updated and modified, and it's not necessarily complete, although there is a lot of evidence in support of this model. Now, according to the standard model, there are only three types of what we call fundamental particles in the universe. And by fundamental particles, I mean particles that they themselves are not made up of anything smaller. Okay, so these three types of particles are called leptons, quarks, and gauge bosons. Okay, all other particles consist of either these particles or some type of combination of these particles. Okay, and so the first type of fundamental particle we're going to talk about is called the lepton. Now, just one more thing about the standard model before we move on. The standard model is a good scientific theory. Now, remember that a scientific theory is supported by experimental evidence, and you cannot prove anything in science, but you can support your scientific theories with evidence. But it has its own limitations. One of the big issues with the standard model is that there's not really a connection with gravity included there. Okay, so with that being said, let's move on to talking about leptons. Okay, now this chart right here appears in the IB Physics Data booklet. There are 6 leptons, and here are the 6 leptons. In this chart you can see that 3 of the electrons have an electric charge of -1e. Okay, we'll talk more about what that e represents later. Okay, but let's say -1e, and then the other 3 leptons have 0 charge. Okay, so let me write out the names of these 6 leptons. We have the electron, okay, by far the most common lepton in existence. We have, this is the Greek letter mu, this is the muon. We have this fancy looking T thing. This is called a tau particle. I guess you could also call it tauon if you wanted to, but I'm just going to call it tau. That's TAU. TAU. Okay. We have, this looks kind of like a V, and I know it looks like a V on here, but it's actually the Greek letter nu. We have nu E. This is called an electron neutrino. We have nu mu. That is called a muon neutrino. And we have nu tau. That is called the tau neutrino. And these are the 6 leptons. The top 3 have a charge of -1. The bottom 3 have a charge of 0, but all 6 are leptons, and all 6 have a lepton number of 1. Okay, now if you're wondering what the heck is a lepton number, we'll talk about that here in a minute. Okay, but they all have a lepton number of 1. Now, in addition, because basically all particles have an antiparticle, in addition to these 6 leptons, there's also 6 antileptons. Okay, and I'm not going to write all of them out, I guess, but the way you represent an antiparticle in physics, there's 2 ways to do this. The most common way is to put a line over it, like so. Okay, and so this would be the anti-electron, or sometimes you see it written like this, E with a plus symbol, because the normal electron has a charge that's -1. An anti-electron, which by the way, remember an anti-electron is a positron, right? An anti-electron is sometimes written like this, and so you do need to be familiar with both of those notations. Okay, these 2 represent the same thing. Anti-electron, positive electron, positron, those are all the same thing. And likewise, you would also have the anti-muon, the anti-tau, the anti-electron neutrino, the anti-muon neutrino, and the anti-tau neutrino. Okay, so on the left we have 6 leptons, on the right we have 6 antileptons. The leptons have, either a charge of -1 or a charge of 0, but they all have a lepton number of 1. And the anti-leptons, okay, the top 3 would have a charge of +1, the bottom 3 would have no charge, and they would all have a lepton number of -1. Okay, so those are the leptons. Okay, so pause it there if you need to add this to your notes. This chart would be good to put in your notes, although I will tell you this exact chart is in the IB Physics Data Booklet, so just keep that in mind. Okay, so some fun facts about the leptons. I'm going to erase this. Okay, so of course the ones we've talked about before are the electron, the anti-electron, that is the positron, and we've also talked about their respective neutrinos when we talked about beta decay. We've actually seen the electron neutrino and the electron antineutrino before, because those have to be included in both beta plus and beta minus decay. And actually we'll see in the next few minutes why they have to be included in beta plus and beta minus decay. Okay, so just some fun facts about the other leptons. The muon and the tau are both highly unstable particles. The muon is about 200 times more massive than the electron. I said before it was discovered in cosmic rays. It is unstable. It tends to decay into an electron and 2 neutrinos in approximately 2 microseconds, which is a very short amount of time, but it is measurable, and without getting into too much detail about how you can measure something that exists for such a short amount of time, it has to do with the fact that muons in cosmic rays tend to move pretty fast, and because of relativity, the faster they move, basically the longer it takes for them to decay, and so we're able to measure muons in cosmic rays, even though a muon on its own would decay in about 2 microseconds if it was not moving. The tau is even more unstable. It's massive, 3,500 times the mass of an electron. It wasn't discovered until the 1970s. Okay, so think about that. The electron was discovered in the 1890s, and then, almost 100 years later, the tau was discovered, and it is extremely unstable. Okay, even more so than the muon. Okay, then you have the 3 neutrinos. All neutrinos basically have 0 mass. And a neutrino only exists with, or only interacts with two forces: the force of gravity, which is super weak because it basically has no mass, and the weak nuclear force, which is also super weak, and very, very short range. And so what that means is because they don't really interact with too much, they basically pass through most matter, and are very difficult to detect. In fact, every second, about 100 trillion neutrinos pass through your body. Okay, neutrinos tend to be generated through fusion reactions in the sun, and a lot of them go through the Earth and through your body, and you never even notice. But every second, as I'm talking, every second that passes, hundreds of trillions of neutrinos are going through your body without you even noticing. And again, the reason you don't notice is because, well, they only interact with gravity and the weak nuclear force, and because most of the atom is empty space, and because those forces themselves are very weak, it's very unlikely for them to interact with anything, much less on a big enough scale for you to notice. Okay, so, and just to show you how many neutrinos that is, over the course of a normal human lifetime, almost a mole of neutrinos will have passed through your body. Okay, so, by the way, in case you're wondering, like, why do we even know about neutrinos if they're so hard to detect, that's its own interesting story, but basically they were predicted to exist in order to conserve momentum and energy, because well, without getting into too much detail, that's basically why they were predicted to exist, and they were eventually discovered through experimentation years later. Very, very sensitive experiments because, again, neutrinos are so hard to detect because they don't really affect too much, unless you're looking over a really wide space over a long time period. Okay, so anyway, let's talk about conservation laws, and these are going to be critical for doing most of the problems that you'll see in this unit. Okay, so conservation laws, the way conservation law works, and we've seen some conservation laws before, is basically you have some type of quantity that is conserved, meaning fixed, that is the same both before and after something happens. Okay, in other words, you can think of it like an equation with two sides of the equation, and whatever this thing that is conserved, it has to be the same amount on both sides. Okay, and so these are some of the conservation laws we're going to be using to solve some problems. Okay, conservation of charge, conservation of lepton number, conservation of baryon number, and conservation of strangeness. Okay, now the last two we'll talk about later. For now, let's only focus on the first two. And basically what we discovered over many, 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 many years of looking at different types of reactants or reactions and seeing what's possible and what's not possible, we've basically come up with these rules that allow us to predict whether or not a reaction is possible or not. Okay, and so conservation of charge and conservation of lepton number, we will start looking at those first. Okay, now remember that all 6 of the original leptons have a lepton number of +1, and all antileptons have a lepton number of -1. Okay, now there's 3 families of leptons. Okay, there's the electron family, the muon family, and the tau family. Here's what I mean by that. Okay, what I mean is that the electron and the electron neutrino are in the same family. The muon and the muon neutrino are in the same family. And the tau and the tau, wow, the tau and the tau neutrino are in the same family. Okay, so lepton number has to be conserved on both sides of a reaction in order for that reaction to be possible. Okay, the total charge also has to be the same on both sides of a reaction. But not only does lepton number have to be conserved overall, but it also has to be conserved by type or by family. Okay, in other words, the electron lepton number has to be the same on both sides of the equation. The muon lepton number has to be the same on both sides of the equation. And so we'll do some examples and so you can see exactly what I mean by this. But a lot of the problems we'll see from this unit that have to do with these conservation problems basically come down to assessing whether or not a reaction is possible or feasible by seeing does it violate any conservation laws. Okay, if it does not violate any conservation laws, then it's a possible reaction. Okay, it should be observable at some point in the future. Now, if it does violate a conservation law, then it's never going to happen. Okay, so we're going to do some examples now to finish up the video, assessing whether or not these reactions are possible or not. Okay, so let's take a look at this. Okay, so example 1, we're given a reaction, and this reaction looks like this. We have a muon, and it appears like the muon is decaying into, wow, that was a bad new, is decaying into a muon neutrino plus an electron plus an anti-electron neutrino. And we have to assess, is this reaction feasible based off of the conservation laws we've seen so far? Okay, now first of all, let's take a look at conservation of charge. Now, the charge of a muon is -1. The charge of a muon neutrino is 0. The charge of an electron is -1. And the charge of a anti-electron neutrino is 0. Since we have -1 and -1 on both sides, conservation of charge is not violated. Okay, now, does that mean this reaction is definitely going to happen? No, because we have to check all of the conservation laws. Okay, so now let's take a look at lepton number. Okay, first let's look at the overall lepton number. Alright, now overall lepton number, remember that a lepton has a lepton number of 1, so this muon would have a lepton number of 1. This neutrino would have a lepton number of 1. This electron would have a lepton number of 1. And then this anti-electron neutrino would have a lepton number of -1. Okay. Now you might be thinking at this point that because it's the same on both sides, that this reaction is feasible. Okay, because lepton number is conserved on both sides. But remember that lepton number also has to be conserved by family. Okay, and what I mean by that is this. Okay, so I'm going to move this box so you can see the breakdown of this reaction. Okay, you can think of it like this. The muon has an electron lepton number of 0. The muon has a muon lepton number of 1, and the muon has a tau lepton number of 0. Okay, why does it have a muon lepton number of 1? Because it's in the muon family. Same thing with the muon neutrino. It has an electron lepton number of 0. It has a muon lepton number of 1 and a tau lepton number of 0. Okay, the electron has an electron lepton number of 1 and 0, 0 for the other numbers, and then you can see the anti-electron neutrino would be -1, 0, 0. Okay, and if you look really carefully, then you'll see that this reaction is feasible because all of these equations are equal on both sides. Okay, so this is a feasible reaction because lepton number is conserved by type. Now, if I were to change, for example, let's say I made this neutrino, let's say I made it a muon antineutrino, then what would change is instead of the -1 being here, the -1 would be here. And then this reaction would not be feasible because this equation would then be 0 equals 0 plus 1, and 0 is obviously not equal to 1. And plus it would also violate muon lepton number because then we would have 1 equals 1 plus -1, and 1 does not equal 0. Okay, so the reaction as written is actually a feasible reaction, but I could very easily make a small change and change the type of one of these leptons and throw the whole thing off. Okay, so we have assessed that this reaction is a feasible reaction because it does not seem to violate any of the conservation laws we've talked about. Now there's two other conservation laws, baryon number and strangeness, but neither of those apply in this situation. Okay, so we are good on this example. Pause there if you need to look at that some more. Okay, so let's take a look at example 2. Okay, so example 2 says look at the decay of a neutron into a proton and the electron as shown below. Is charge conserved and is lepton number conserved? Okay, so we have a neutron decaying into a proton and an electron. Okay, and so if we want to determine whether or not this reaction is possible, we need to start with our conservation laws. Let's start with conservation of charge. Now, a neutron has a charge of 0. By the way, make sure you don't confuse a neutron with a neutrino. Both of them have no charge, but they're completely different particles. A neutron has a little more mass than a proton, whereas a neutrino basically has no mass. Okay, a neutron, as we'll see later, is a baryon, and a neutrino is a lepton. Okay, so don't think just because they both have no charge that they're the same thing, because they're completely different. Okay, don't confuse a neutron and a neutrino. A proton has a charge of +1, and the electron has a charge of -1. Okay, so just going based off of conservation of charge, this reaction is feasible. Okay, now let's take a look at lepton number. Okay, now the lepton number of a neutron, we'll talk more about the neutron later, but the neutron is not a lepton at all. Okay, it's not one of the 6 particles we talked about, so its lepton number would be 0. Likewise, the proton has a lepton number of 0 because it is not a lepton. And the electron, which is a lepton, has a lepton number of 1. Okay, so now we have an issue because 0 is not equal to 1. And so this reaction as shown is not possible because lepton number is not conserved. Okay, so for example 2, we would say that this reaction is not feasible because it violates conservation of lepton number. Okay, now if you think to yourself, is there anything I could do to this reaction? Is there any other product I could have that would make this reaction feasible? And there is actually. Pause it here if you need to write this down. I'm going to erase this. Okay, as a matter of fact, the reaction as shown was not feasible, but it would work if you added an anti-electron neutrino. Okay, because then, as far as lepton number is concerned, we would have 0 equals 0 plus 1 plus -1. Okay, and so the anti-electron neutrino gives us a lepton number of -1 that is required in order to conserve lepton number. Okay, now the reason it has to be an electron neutrino is because remember lepton number also has to be conserved by family. Okay, and so if that was an anti-muon neutrino, it might conserve lepton number overall, but it would not conserve lepton number by family or by type. Okay, now what we're seeing here is that in this particular reaction, the only way that it works, okay, that the only way it does not violate those conservation laws we talked about, I don't know why I wrote an N, is if we include as one of the products an anti-electron neutrino. Okay, and as we'll see later, this reaction is actually beta minus decay. Okay, beta minus decay happens in a nucleus when you have too many neutrons, and one of the neutrons turns into a proton. And because it turns into a proton, in order to conserve charge, it also emits an electron at the same time. And then in order for lepton number to be conserved, it also emits an anti-electron neutrino. Okay, and so this is actually a beta minus decay at the most fundamental level. Okay, a neutron turning into a proton. Well, not the most fundamental level. We'll actually see beta minus decay in even a more broken down form later on. Okay, but this is an example of beta minus decay. Okay, now we see for the first time why in beta minus decay you have to have an anti-electron neutrino. Okay, it's necessary in order to conserve lepton number. Alright, so we've now done 2 examples. I want you to try to do the next 2 on your own, or the next page on your own. Okay, so take a look at example 3. There's 3 reactions here, and I want you to determine whether or not these 3 reactions are possible. Okay, if they are possible, that's good, and if they're not possible, then explain why with reference to the appropriate conservation laws. Okay, so I will leave these 3 for you to answer, and As always, please let me know if you have any questions, and I will see you guys in the next video.